Hi folks, my name is Jeff Talkington. I'm a systems engineer for Palo Alto Networks. Today, I'm going to be giving you a demonstration of Traps Advanced Endpoint Protection. Before I jump into the demo, we need to discuss what Traps is and why it's the right solution to replace legacy antivirus and even next-gen AV solutions. I promise, I'll keep the slides to a minimum, but we do need to talk about how an attacker targets your endpoints and the methods we use to prevent successful cyber attacks. Let's take a closer look at a typical attack sequence to help us better understand why endpoints continue to be compromised. A typical attack sequence starts with the attackers conducting reconnaissance on your organization and potentially on specific individuals they want to target. Next, attackers compromise one or more endpoints to gain a foothold in your organization from where they can launch the remainder of their attack. Once they have compromised an endpoint, attackers can establish a channel to their command and control mechanism to retrieve additional instructions, download malware, or carry out other actions to pursue their objectives. So compromising an endpoint is often the first step in an attack. Let's turn our focus on what attackers do to compromise endpoints. There's essentially two phases or two steps in compromising an endpoint. First, the attacker must deliver a malicious agent to the endpoint, then carry out one or more malicious actions to compromise the endpoint. And attackers have many options for how they carry out these two steps. They can deliver their malicious agent using web-based exploitation, where the attacker delivers an exploit like a weaponized data file or a data stream through a malicious or compromised website. A malware download, where the attacker gets the user to download a piece of malware. Or an email attachment, where the attacker sends the user an email attachment which might be a piece of malware, a data file containing an exploit, or an Office file with a malicious macro, a malicious script, or some other malicious attachment. After delivery, the attacker has multiple options for malicious actions. They can run malware, run macros that are embedded in Office files like Word and Excel docs, run scripts like PowerShell, JavaScript, or others, exploit good applications, or exploit the operating system itself, and escalate their privileges so that they can hijack system processes and resources they normally wouldn't have access to. In order to be successful, an attacker will typically combine several of these methods. Let's use ransomware as an example. As an attacker, I might start with a Word document embedded with a malicious macro being delivered as an email attachment. The user opens a document and gets tricked into activating the macro. The macro launches a PowerShell and runs a script. That script downloads additional malware and runs it on the machine to encrypt the user's files and demand payment. So you can see that as the attacker, I combine several methods to effectively carry out my attack. These methods that I use fall into one of two categories. The first is exploits. Exploits are vulnerabilities in otherwise legitimate programs like Microsoft Word or Adobe Flash. These vulnerabilities or bugs in the program allow malicious code to be executed. The other category is malware. Malware is a malicious executable that is freestanding and doesn't need a legitimate program to run. The distinction between these categories is important, and I'll show you why during the demonstration, as we can use either exploits or malware or both to successfully compromise an endpoint. So this is the challenge presented to companies that offer security solutions for endpoints. In order to be effective in preventing successful cyber attacks, we need to have solutions for all of these methods. Many legacy AV vendors only do one of these effectively. Many of our competitors will only have solutions for a few of these, and many don't even address exploits, claiming they're just delivery vehicles for malware. I'll show you in the demonstration why exploits are dangerous all by themselves, and why protections for all of these categories are essential. Let's start by looking at how we prevent malware. To prevent malware that has been seen elsewhere, Traps uses Wildfire. Wildfire is our cloud-based threat intelligence and malware analysis system. Wildfire takes in information from our 40,000 plus customers, our partners, and multiple third-party sources to push protections to all Palo Alto Networks products. When Traps encounters an executable that it doesn't know, it queries Wildfire with the hash of that executable file before the file is allowed to run. If the executable is deemed malicious, Traps automatically terminates it, reprograms itself to prevent the execution of that file from that moment on, and optionally quarantines it. To prevent unknown malware from compromising endpoints, Traps uses local analysis via machine learning to instantly determine if an executable file is likely to be malicious or benign. Traps examines hundreds of characteristics of a file in a fraction of a second to render a verdict on that file before it's allowed to execute without relying on signatures, scanning, or behavior analysis. We use the threat intelligence available through WildFire to train a machine learning model to autonomously recognize malware, especially unknown variants. The analysis of the unknown happens on the local machine, hence the name local analysis. This is especially useful if users are not connected to your organization's network and can't take advantage of WildFire. In addition to using local analysis, Traps also submits an unknown file to WildFire for full analysis. WildFire goes beyond traditional sandboxing approaches used to detect unknown threats. It brings together 4 independent techniques: dynamic analysis, which involves running an executable in our custom-built sandbox to observe its behavior; static analysis, which analyzes characteristics of the file to determine if it's likely to be malicious; machine learning, which extracts features from the file and evaluates it against a model to determine if it's malicious; and finally, bare metal analysis, which runs the executable on actual hardware. This is something that's unique to WildFire and can identify even the most evasive malware. And WildFire accomplishes all of this in as little as 5 minutes. Traps also provides a malicious process control capability that gives our customers fine-grained control over the launching of legitimate applications like script engines and command shells. We can blacklist or whitelist applications, helping us to prevent scripting or macro attacks. Traps delivers endpoint prevention using a multi-method approach similar to the malware side. Traps can actually prevent an exploitation attempt before it can start by blocking the vulnerability profiling attempts that exploit kits use. This profiling is sometimes called fingerprinting, which is the process of collecting information about an endpoint before initiating an attack so that the exploit kit can identify specific operating system or application vulnerabilities and match the optimum attack to leverage those vulnerabilities. In addition, Traps uses a unique technique-based approach to preventing exploits. Traps prevents both known and zero-day exploits by blocking the exploitation techniques attackers use to manipulate applications. Although there are thousands of exploits, they all rely on a small set of exploitation techniques that change very infrequently. Traps blocks these techniques, which prevents exploitation attempts before they can compromise endpoints. We'll dive a little deeper into this technique-based approach in just a moment. Traps can also prevent the exploitation of the operating system itself. A very common kernel exploitation technique is to create a malicious process that would steal the credentials of a privileged process, allowing the malicious process to run with system permissions. Traps identifies and blocks this technique, and with it, various other kernel exploits. And because Traps is an integral part of the Palo Alto Network's next-generation security platform, it still benefits from the platform and its capabilities. As I mentioned earlier, there are a number of sources that feed threat intelligence into WildFire. These include various third parties, industry sharing services, and tech partners, as well as other Palo Alto Networks customers and their Palo Alto Networks technologies that they have developed in their environments. All of this threat intelligence is captured in WildFire. WildFire analyzes this threat intelligence using its multi-technique approach and delivers prevention controls to Traps. More specifically, Traps customers can block malware that has first been seen elsewhere by other Palo Alto Networks customers on any of their Palo Alto Networks components, whether it's a next-generation firewall, Aperture SaaS Security, or Traps, and you don't have to deploy any other Palo Alto Networks components in your environment yourself to get the benefit. And there's another major benefit. And that's the training of our local analysis machine learning model that I mentioned when we discussed Trap's multi-method malware prevention approach. The machine learning model is trained using the threat intelligence in Wildfire. And as that model is updated and becomes more and more effective, you get the benefit of that improvement automatically. Now that we have an understanding of the value of traps, let's jump into the demonstration. For our demo today, we'll be playing the role of the attacker and launching a ransomware attack against our victim machine. We'll be using 3 systems in this lab. The first is our attacker machine. It's running Kali Linux, which is a tool used by security professionals to test exploits. It's the only way we can legally launch these types of attacks. The second machine is our ESM server. Now, ESM stands for Endpoint Security Manager, and it's what manages each of the Trap's endpoints within the enterprise. You'll see that we're starting with protections disabled to each of our endpoints. This is so we can prove to you that the exploits and malware we're using are real. As we launch a successful ransomware attack, we'll go back and turn on protections to show you the power of traps. The third machine here is our victim machine. It's a Windows 7 box with traps installed. You can see on the traps console that protections are disabled. Now, this console is not normally up. Normally, you'll just see the small icon in the lower right. But we've gone ahead and opened up the console just so you can see the status and see that protections are in fact disabled. Now that we've looked at those 3 systems, let's go back to our attacker machine and let's start our ransomware attack. Today's ransomware attack is going to be a Petya variant that we're going to deliver using a weaponized website that I've created that's going to look and feel like a normal website, but we're going to take advantage of a flash exploit in order to gain access to a system. So let's get started. The first thing I'm going to need to do, since we're using a web server, is start my Apache web service. The next thing I'm going to do is start up MSF console with a script that I have running. This will start the Metasploit framework console, which will load Meterpreter. And you can see what I've done here is I've decided to use this exploit here. It's a flash exploit from Hacking Team. And then what we're doing is we're listening on this IP address and this port and this URI in order to get a connection from our victim so we can take control. So we're up and running, we're listening. All I need now is to get my victim to connect to my web server. Well, the way I'm going to do that is I've sent a spear phishing email to this individual, and we'll see if we can get them to click. Now, the email went to this user, 999cubsfan@gmail.com. So in order to lure this person into clicking, I've decided to go and craft an email that makes it look like we're going to offer some season tickets to my victim's favorite team. So I've put this link into the email here that looks like a normal email. We're going to have this person click on it. So once the user clicks on it, you'll see on my attacker PC, we've got some activity here. We've sent an HTML response page. We've also sent a flash file, and what we see is a connection comes back and the Meterpreter session opens to my victim. But on the victim machine, I've gone to a web page that looks relatively normal. I don't have any warnings, nothing's going on. This looks like a legitimate website, all right? I've taken some legitimate content, and this looks real. This victim can even look around, click on links, all of that, and they think everything is normal. But in the background, as an attacker, I own this system. Now, the thing to take note of here is that at this point, all I've done is use exploits. So for our competitors that say we don't need to worry about exploits, that all we need to worry about is malware, I respectfully disagree. At this point, all I've used is exploits, and I completely own this system. From here, I can establish a beachhead where I can load malware if I want to, or I can simply sit here, stay in the shadows, gather information, gather intelligence, and launch a bigger, deeper attack into somebody's network. So just to show you that I do in fact own this system, Let's see what sessions we have open. So we've got one for our victim machine. So let's go ahead and start an interactive session with this machine. So I'll go into session 1. So I'm into an interactive session here. Let's take a look and see if we can find some information on this system. I'm going to use PWD, and that's going to show me the directory that I'm currently looking at. All right, so we're in the desktop directory. I can also find more information, find processes. I can execute commands as well. So for example, we'll do an execute -F. We'll try to open up the calculator from here. So I did calc exe, which is a calculator, and you can see that the calculator is opened up. So I own this system, okay? So the next thing that I'm going to do is I'm going to move my piece of malware over, and then I'm going to remotely execute it. Now the thing to know is that in a normal ransomware attack, this wouldn't be quite so manual. This would obviously be very automatic and very scripted, right? So, but what we will do is let's go ahead and upload. We're going to upload this happy.exe. This is our Petya ransomware. So we'll do upload from our desktop. Happy.exe. I love the name of that. And we're going to move that over to this directory that we've created, that we know that we're working in on our victim machine. This is why I've looked this up. I've got to do double slashes here. That's just part of Kali Linux. So we'll move this over to the desktop. Okay, so we've uploaded that file. And if I look on the desktop here, we can see we have this new executable that's moved over. Obviously, if I was doing a real ransomware attack, I would create someplace or move this someplace that was much more hidden than it is. But the point is, at this point, I can do a remote execution of this piece of malware as well. So let's do that right now. Let's do an execute of happy.exe. We execute on that, and we see immediately my virtual machine has rebooted, and this is starting to do the encryption process. Okay, so this is bad. This is really bad, right? So, and if we try to reboot, we get the flashing skull and crossbones. I've been owned. I've got this piece of ransomware, right? I'm completely infected. So this goes to show you that we're using real exploits, real malware. So let's reset the lab, and then we'll show you exactly what happens when we put traps in place and we're protecting all of our endpoints using traps technology for both exploit and malware prevention. All right, we've reset our lab and we're back to normal. We've got our attacker machine up and running. I've got my exploit ready to go. I've got my weaponized web page all set. What I have changed here is that we're now enabled with traps protection. So we're doing our anti-exploit protection, anti-malware, and we're collecting all our forensic data. Okay, so we're all set there. What we're going to do now is I'm going to launch the same attack, and we're going to see how traps responds to this. So from my spear phishing campaign, I've got the same email up. I'm going to click on this link. You're going to see on my attacker PC, we're sending the HTML file. We tried to send the flash file, but oops, traps pops up and says it's detected a malicious activity. Specifically, what it's saying is that it sees a suspicious access to DLLs attempted. So if we say OK, this will try several more times. This is the nature of Internet Explorer in doing several retries. But you'll see that we blocked that initial exploit attempt. Now if we want to take a look and see what that was, we can go over to our trap server and we can look at our security events. And again, this retried several times. So we'll take a look at this. We can see this actual event, exactly what happened, and we can pull all the pertinent information. We can see that this was in Internet Explorer, who the user was, what the operating system was, all of that real good juicy information that we'd like to see when we have a ransomware attack. What the IP address was, all of that great stuff. Now, this was one exploit that we've prevented. Throughout the course of this ransomware attack, there's actually 3 exploits and several malware attempts here. So if I want to disable a rule, if I want to disable an exploit prevention, let's say we have what we believe to be a false positive, I can create a rule here by simply clicking on this button, and we can turn off that DLL security. So we'll apply that prevention, we'll apply that exception here to our policies. And if we look at our policies, you can see that we've turned off DLL security for Internet Explorer on this particular system. So what I'm going to do is we're going to reset, and we're going to try this again. You'll see this is still retrying, but let's open up Traps. We'll check in again. Now by default, Traps checks in about every hour. This way I'm manually checking in, and I can pick up that latest bit, the latest exclusion that I've just done, the exception rule that I just created. And remember to take note that the first protection that we saw was for DLL security, for DLL hijacking. Let's see what the next version of this is. Like I said, there are 3 exploits that get used for this particular piece. So we'll jump back into our email. We'll click on that link one more time, and we'll see what happens. You'll see that we are making that request again. We're sending the flash file again, or we're attempting to, from our attacker machine. But we were stopped again by Traps. But you'll notice the prevention description here is different now. We're saying ROP chain utilization attempt detected. ROP is return-oriented program. It's a memory exploit that gets used. As I said, there are 3 of them here. So we've stopped this. We've stopped the second exploit attempt as well. I'm going to go ahead and create another. We'll do another exception rule, and we'll look for the third one as well. So let's close this. We'll go back over to our ESM server, look at our security events, and let's pull the latest one here. You'll see that we had this one for the ROP mitigation. And what we will do is we will create an exception rule for that. So I'm going to turn off protections for ROP mitigation as well. We'll look at our policies. So I've created 2 exceptions here, one for the DLL protection module, the other one for the ROP mitigation module. We're going to check in one more time, and then we'll try this again. And you'll see that we have a third exploit that we should be hitting. We'll go back into our email. We'll click on our link one more time. You'll see on the attacker, we're sending one more time. We tried one more time, but again, we were stopped. And again, the prevention reason changes. In this case, it's a suspicious API call from an unsafe code. This is the JIT mitigation module that gets nailed as well. Again, this is another memory exploit technique that gets used. All of these are designed to load malicious code into memory spaces in order to execute that code and give me that access. So what I'm going to do, I'll create a third exception rule. And when we come back, I'll reset and we'll look at the malware portion of this and how we prevent that. Okay, so we've reset, and what we're going to look at now is the malware prevention side of this. In order to look at malware prevention, we've completely disabled our exploit preventions. We've got 3 policies in here in order to disable our exploit prevention modules. And that's something to take note of. Most ransomware uses at least 2 and usually 3 particular exploits in order to be able to move a piece of malware onto a system and then execute on it. So what you need to understand is that in order to be successful, in attacking a traps protected machine, you have to come up with a brand new exploit prevention technique. Not just an exploit, not just a vulnerability, but a brand new technique, because that's what traps focuses on. So in order to be successful, you would have to come up with a brand new technique that's never been seen before. And just to give you some idea of scale, we normally only see 1 or 2 new techniques come out every year, and those usually come from academia. All right. So it's extremely tough to do. But we've gone ahead and turned off our exploit prevention modules. Obviously, I wouldn't recommend you do that in a production environment, but we've done that here just to see what will happen. So I've got my exploits running. I've got my spear phishing campaign is out there. My email is ready to go. So let's click on the link. Let's see what happens. We're sending the HTML. We're sending the flash file. And you see this session opens. So my exploits are working. And I've been able to create this interactive session. So let's do like we've done before. We're going to come into this session, this interactive session. We'll upload our file like we've usually done. If we look here, we can see that happy.exe lives on our desktop now. And we can try to do a remote execution. All right, so we tried a remote execution, but traps nailed us again. So even though we've turned off all of the exploit preventions, we're still getting nailed. Okay, so the big question is what's preventing this, and that's going to be our malware prevention. So let's take a look at our trap server. Let's take a look at our security events, and you can see here we didn't even have to hit the malware modules. In this case, we hit our Wildfire hash control. Now, Wildfire is the threat intelligence cloud, and it's the brains behind everything within Palo Alto Networks. This is how we compile all of our threat intelligence. This is also our sandbox where we do malware analysis. We create verdicts in as little as 5 minutes and send those preventions down to all of our products, not only traps, but our next generation firewall and all of the products within the Palo Alto Network suite. So if we look here, we can see exactly what happened. We've got, obviously, this hit, this was determined to be malware by Wildfire. The way this happens is we send a hash up of this file to Wildfire. It does an immediate check and says, you know what, I've seen this hash before. I know this is malware. Don't run it. Don't allow it to go through. There's one last thing we need to talk about, and that is the differentiation between Wildfire malware analysis and our static analysis. Now, what you just saw was Wildfire picking up on a piece of malware that's been seen before. It's been seen in the wild, and so we know what it is, and we immediately declare it to be malware, and we don't let it through. The big question is, what happens for those 0-day malware? What happens when we change the hash just enough so that Wildfire doesn't know what this is? So let's try to do that. Right here we've got where we can look at the SHA-256 hash for our particular file. And it's this large hex number that we have here. Now, in order to change a SHA-256 hash is actually pretty simple. I'm going to use a standard hex editor, and we're going to drop into this file. I'm going to go to the end of the file, this address here. This is 0x0001D7FF. The way I'm going to do that, we'll do a Control T, go to 0001D7FF. We're going to change this just enough, hopefully, that Wildfire will see this as a brand new file. So we'll do Control X. We'll save it as happy.exe. We'll go to our desktop, make sure we don't have it saved out there. We've still got our session up, so we're going to upload. And we'll try to execute that file again. So we've uploaded on our victim machine. There's that happy.exe. And just to be clear, I changed that hex value. and the hex value is completely different than what it was before. So that desktop happy.exe is a different hex value. It's a different SHA-256 value, which means that anything that is referencing that SHA-256 value is going to think this is a completely different file. So I've loaded that completely different file onto my victim machine, and we're going to execute that, and we'll see what happens. So we execute, and we'll see that it's a suspicious process has been detected. Again, it's going to know that this is still a piece of malware. Even though we changed the SHA-256 hash, this is where legacy AV would normally fall down. Whenever we change a value that changes the file enough, legacy AV would usually miss this completely. But we still know that it's a piece of malware, and we're still going to stop it. So let's look at our server, and we'll see that it's still hitting the wildfire hash control. We still know that when we send this up, we still know that this is a piece of malware, even when we change it, even when we do something different, even when we try to do something that's a little off, right? We're still going to know that this is a piece of malware.